to you, and I do promise I will get back to you, but it is not today. But if anyone wants to walk through that logic to start us off, they can.
I think I kind of get it.
Do you want to share your screen if you have it, or if you want to work through it, or do you want to save it till next Tuesday?
Yeah, I just need to switch computers, but I can share my screen.
Okay. Also, I
Just
can
give me
stop
like,
sharing then and let you do it.
yeah, just give me 1 sec.
It's really a bad haircut. Like, not that the hairdresser had a lot to work with, but still.
You got a bad haircut?
Yeah, I don't look at myself unless like I'm staring at a fucking Zoom window, right? So.
Sorry, I'm just grabbing the link on my laptop from the syllabus.
Well, John, at least you don't have to worry about the split ends and everything. It's a fine haircut.
Yeah, it's true. The nice thing is you can't see the back of my head when I'm staring at the Zoom, so you don't see my bald spot. And the grays are mostly over my temples instead of my front, so it's still okay.
Yeah, and anyways, you can go bald and go crazy and maybe keep spikes. There are always a lot of options until everybody has any hair.
That's true. That's true. I do have options when I have hair. Okay. So, Paul, do you want to work us through this? These at the final center.
Yeah, sorry. I couldn't find the unmute button. But pretty much like what I thought of was that where the hell is it? If you I guess I can just do it from here, but pretty much what I thought was that if you like carboxylate that end, like from going from the xylose,
yeah,
whatever, this becomes meso, because there's like an internal mirror, and then yeah, it's not octavely active, and we know that this
is
octavely active. Yeah, so that can't be the structure.
I think you're right. I think that's exactly it. I'm going to double check it, but I think that is correct. It's based on the fact that one of them's optically active.
Yeah, like because you would have to change. It's this carbon, so this would be flipped the other way, and then you would have like unless I'm misunderstanding.
I think it is that carbon we're talking about. No, I think it's the one up.
Yeah. Okay. Yeah, it's this one. Sorry.
Yeah.
So if you flip that one, then it's symmetrical and then not octavely active.
I think it's the one in the middle, actually, but yes. Okay. Yeah.
Oh.
But still. Okay.
Yeah.
We'll cover this again on Tuesday because I really want to make sure I get the proof right, and I've just had a silly day, and so I didn't get to going over it again. I started sketching stuff out, and I was kind of following that same logic, and I want to triple check it before I actually put it into the notes, because then it's like real, and I'm in trouble. Okay, so lecture 3. What we're going to really talk about today, I want to talk about two things, really. It's going to be conformations of sugars and the anomeric effect. So I guess the question I've got for the class is who's familiar with the term stereoelectronic effects? Is anyone familiar with the term stereoelectronic effects?
I've heard you say it before.
Well, it is the fact how electrons in the compound of the molecule behave because of the stereochemical properties. Simple, I guess, but it's It has to do with the temporal and the spatial controls. I just read it somewhere. I don't know.
Okay.
Yeah.
Susanna?
Sorry, you asked if we know what
Yeah.
stereoelectric effect is. Um, that I think it has something to do with uh whether like the switch between axial and equatorial.
Hmm.
If
It actually influences that significantly, yes. Um, it's got nothing to do
whether
with really axial and equatorial necessarily. Cool.
okay.
Okay, Kirsten or Ashley? You're not as much on the spot because those guys are all grad students.
Well, I feel like I've heard the two words separately, stereo.
Yes, absolutely.
So I would agree with Samra in that I feel like it would have to do with the how the stereochemistry affects the electronic properties of
And
a
you're both geniuses. Yeah, like you're right. We're gonna get into some detail on that. I just want to know what kind of familiarity. And Ashley, at all familiar?
Just from hearing the terms, like I wouldn't be able to put them
Okay.
both together, but
Cool.
it sounds great.
Okay, I just want to know where we're at, and so I think we're more or less on the same spot. We're not super familiar with this. Okay, so that's really anomeric class, anomeric effect. I guess I said class, and I was thinking class. Okay, that's cool because that's actually it explains a lot, and we're going to sort of see that of chemistry in general. So let's just think about confirmation for a second.
sorry, Tran.
Yeah.
I just wanted to let you know that we can. I don't know if everyone else is getting
I'm
this.
not sharing my screen. Yes, absolutely. App. Thank you. Keep. Yep. 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 You know, you think after like a term of doing this, I'd actually have figured all this stuff out, but no, really haven't. No idea what I'm doing. Um, thank you. Yeah.
But you
So
never
please.
had those bad days where you would have recorded, half of the lecture and no, yeah, half of the lecture was gone without the recording.
That hasn't happened to me yet.
That's good, very good.
Yes. Yeah. Exactly. And this was, and then of course, what I did first thing when you said that, Summer, is I looked down to make sure this was recording.
Awesome.
So, if you need to practice drawing chairs, please re-practice drawing chairs, because otherwise you draw what I just drew, which isn't a chair.
Yeah, actually, I found a very funny trick. On the camera, they have this good template for all these sugars, so everybody can save some time.
Yeah, you're very welcome to use the ChemDraw templates if you like to draw. That's fine. Um, the reason I one of the reasons I actually draw stuff out isn't because I couldn't pre-prepare this stuff. I've got it all prepared. I could have copied and stuck it onto slides. But one of the things is just the pace is a bit more controlled if I have to draw, because otherwise I might go too fast, and that gives us all a chance. And it also makes sure that I think you're drawing. I am going to be posting all of the slides probably first thing tomorrow morning. I don't think I've posted the first two lectures yet. I will post them. I'll post this one. I'll try and post them the morning after class, mostly because at 5:30 I try and quit for the day under normal circumstances, because my wife tells me she's going to divorce me if I don't spend the evenings with her, and that would really hurt my productivity. And so, in the interest of avoiding divorce, I will probably generally be uploading these things the morning after instead of later the evening. So
That's good. That's fine with us, I guess.
yeah, exactly. So what I'm trying to draw, again, just a reminder with a chair. So this is the acetate protecting group, and if you can't quite remember what that is because it's been a little while, AC equals that. It's basically, it's like acetic acid without the alcohol, the OH of the acid, because the OH of the acid is drawn in there already. So again, what we're trying to do here, just as a reminder for drawing these things, is everything is just sets of parallel lines. All those blue lines are meant to be parallel, along with that one. I'm a really bad drawer, so they're not perfectly parallel, but you can sort of see that in spirit, I'm trying to make them parallel. And then I've got these orange lines, and these guys are all parallel. And then the remaining red lines are parallel. This guy, I guess, should be blue, though, the one leading up to the C6, but it's not part of the real ring. It's not part of this axial equatorial thing anyways, so I guess it really doesn't count. But I always try and draw that one parallel. So what we're going to call this, sure, I like maroon. Maroon's a good color. This is the C41 Confirmation. Okay, so what the hell is going on there? So it's C, that stands for chair. And we know, and so, but there's two different chairs for any given cyclohexane or six-membered ringy thingy, because you can ring flip it, right? So in this one, the carbon 4 is up here, carbon 1 is here. The oxygen doesn't get a number, so carbon 1 is that anomeric carbon that we were talking about, the one that's attached to two oxygens. I'm not gonna try and confuse you, and I'm not gonna try and confuse me, so I'm generally gonna draw my sugars like this whenever I possibly can. And the 4 carbon is kind of, up, like it's poking up. The 1 carbon is kind of poking down. So 4 up, 1 down. So this is the 4C1 glucose. And the C stands for chair. And this, of course, is in rapid equilibrium, although not particularly favorable equilibrium, with the other chair. So we ring flip, and whenever you ring flip, one good cheap way to do it is slide every atom over, either one clockwise or one counterclockwise. Keep all your ups up, all your downs down, all your equatorials become axial, all your axials become equatorial. Everything was equatorial, so now everything is axial. It's glucose, so everything just, you switch every time. My dog is barking in the background. Some kid must be on the street trying to just walk innocently. So, in this case,
Bastard.
Yeah, he is. He's a pain in the ass. I do love him so much. And
Oh, I meant the kid.
oh, the kid. Yeah, the kid's a bastard probably too. So in this case, if we look for carbon 1 and carbon 4, what we find now is carbon 1 is up, kind of pointing up. Carbon 4 is kind of pointing down. So unsurprisingly, this is the C41 confirmation, or the 4C1 confirmation, where the 4 is low and the 1 is high. People will also write this as C14. Both of those, I don't know what the IUPAC approved form for that is. I don't care. I'm not really going to use this terminology too much, but I just want you to be aware of it because it is out there. So you might run into it in some of the papers that we're looking at. So that's the chairs. When we talk about cyclohexanes, especially in second year, we start talking a lot about boats. Boats are really high energy. Boats are silly. Nothing does a boat. So we're not really going to have to worry about boats. But what we do need to worry about is the pseudo boat. Orange is an ugly color. I will get rid of the orange. It's not so much orange as an ugly color. It's just hard to read. I don't know why I don't just use black. I find black, I do. I find black really hard on the eyes. So what we have here is, last class we left off talking about oxocarbeniums. I said, hey, this is an oxocarbenium. This thing's kind of important. So what that as soon as you're doing that, what we have here is we now have 2 sp2 centers in the ring. And once we introduce sp2 centers in the ring, the chair is no longer accessible. You can't make a chair because by definition, this bond, like this atom here, this I've got different colors. Why don't I just use that? This atom here, this oxygen, this carbon, and this carbon have to be coplanar. And of course, in a chair, you don't have 4 atoms all adjacent to each other coplanar. They kind of pucker. That's just the way the chairs do it. So these compounds, when you have this double bond in a ring, cannot adopt a chair. But they don't adopt a boat either, because the boat is also a conformation found from when everything's sp3. It's not the case, but it looks a lot like a boat, so it's a pseudo boat. I'm going to draw a lot of them this way because this is easier. So we're just going to make sure that we're really clear. Again, okay, that was going to happen. I just start pressing buttons too fast. I just want to be clear on what the hell is going on with the stereochemistry in the system. So first of all, there's some substituent here. It's coplanar with everything else, right? Because that's an sp2 center. Here, we're coming back to this whole deleting things again randomly now, are we? On both of these guys, we have a pseudo-axial. It's not quite axial. And a pseudo-equatorial. It's not quite equatorial, but it's actually really equatorial. Like it's almost like perpendicular to the plane. It's much better. It's much more equatorial than equatorial. But because equatorial isn't really equatorial, we call it pseudo-equatorial. Because of course we do. So pseudo-axial, pseudo-equatorial. And over on the terminal one here, I'm exaggerating a bit, but you almost have 2 of the substituents that flip over the top of the boat. And then you've got 2 that are kind of down. And again, pseudo-axial, pseudo-equatorial. If you need to build a model kit to remind yourself of this, that's cool too. How much is it going to matter? A bit. But what these things, sorry, I should have a positive charge on this carbon. I dropped it for no particular reason. What we're generally going to draw these as, though, is as a half chair conformation, which is the more stable form of this. And I hate drawing half chairs. And I just wish it wasn't the more stable form of this. I don't know why this is called a half chair conformation. Okay, so what we're doing is we're looking basically straight on this bond here. And everything there is coplanar because we just said it was. And you can flip to the other half chair. Which is like that. So what we have here is we have 4 of the bonds, all coplanar. One's above the plane, one's below the plane. This is more stable for obvious reasons because look at this guy. Everything is eclipsing everything else in this pseudo boat. It's pretty awful. Here we avoid everything eclipsing everything else. And again, we kind of have pseudo-axial and pseudo-equatorial conformation, substituents on everything. So it kind of adopts that axial equatorial, the up is axial, the down is axial. I guess we're in this place here, so it doesn't make a lot of sense. The up is axial, the down is axial, the up, like you have this going back and forwards, just like a chair does, right? Carbon 1 is axial, carbon 2. If carbon 1 is axial up, the axial on carbon 2 is down. The axial on carbon 3 is up. So you have that same interchanging of things. But that's about where the similarity with the chair ends because it's obviously a really effed up chair and it wouldn't be very comfortable to sit in. So this is the actual confirmation that anything with a double bond in it in a 6-membered ring actually exists as. We are going to come back to this in a bit because we're going to drop it for a few minutes. Actually, a few seconds. Okay. I'm going to change slides. So I'm going to change slides, or I'm going to bring up my Cortana notifications. So let's say we have a sugar, and we're going to have a real simple sugar. It's not really a sugar. It's basically an anomeric center. I'm going to do my best, and I always do, in every single class I teach, to keep my profanity to a minimum and to keep obscenity to a minimum. The challenge I have is I'm profane and obscene. And so if something slips out and somebody feels really uncomfortable with that, please send me an email, and I'll take actual super special caution with it. I do try and keep it under wraps. Just one of the challenges is I just the way my brain thinks, and all my analogies are really dirty because I had a dirty analogy I'm not going to use. And so I just want to give that heads up. So if I'm making you feel uncomfortable, please let me know immediately. Do my best to not do that. It's just I remember things better that way. So, we protonate the oxygen. I don't think there should be a surprise to anyone here. Hopefully. Okay. What happens next? We're going to come back to actually really what happens, because I'm going to draw two arrows and you're going to go, yeah, that makes sense. The lone pair on the oxygen makes a new double bond, kicks out water. There's a lot going on in those arrows. We are going to come back to that. And we get our oxocarbenium. And again, notice that I've now switched from drawing it as a chair to drawing it as one of these pseudo boats, while knowing at all times that this is actually in a half chair, but there's no way I'm going to draw half chairs all the time. And it's only if I'm really trying to think about the mechanism in a lot of detail and some stereochemical outcomes, I'm going to worry about the half chair. Otherwise, you can do as I do and draw the boat. And this is what all sugar chemists do. You'll see this all the way through papers, textbooks, everything. They'll do this because it's just easier. Okay. Now you've got methanol present. And it has two options. We follow the blue arrow, and just from the angle, the methanol is going to come in beta. And if we follow the maroon arrow, the methanol is going to come in alpha. Okay, so I've just made the proton disappear on the oxygen of the methanol. Another molecule of methanol came in and picked up that proton. I don't expect you guys to show proton transfers. You can if you need to keep track. I don't expect anyone's too confused about that. If you are, and it's a bit embarrassing to mention that, please send me an email. We can go over it in detail. I'm very happy to. Whenever I teach this class, I've always got people with massive different backgrounds. So that's cool. Okay. Now, what we've got here is a mixture, and theoretically now you can do, if there's acid present, so this is reversible. Right? Because we protonated an alcohol, added an acid, kicked out the alcohol, boom, all happened. It's actually easier to protonate this ether than it is just that OH. So this equilibrium is actually faster than the initial reaction that we did. I haven't drawn the first arrows in equilibrium, and that's because we're probably doing this in methanol. There's very little water present. So it's unlikely that water is going to be the nucleophile coming back. It is technically in equilibrium. But it's also technically possible that all my atoms could choose to be on the moon in a few seconds. unfortunately for you, I'm going to keep lecturing most likely, and unfortunately for this molecule, it is most likely that the methanol is going to come in, not the water. So I'm choosing not to draw it as an equilibrium with these arrows here, even though technically it is an equilibrium. It's just Le Chatelier's principle suggests that there's so little water present that the methanol is going to dominate the interactions. Okay. So we have an equilibrium system set up. We're under, there's heat here too, lots of heat. Good old fashioned, this is that Fischer esterification that we looked at where, like all German chemistry before about 1940, the secret is mix your chemicals together and heat the crap out of it. And so that's what they're doing. And so you set up an equilibrium between these two molecules. And again, if we're looking at this strictly through a steric analysis, and by a steric analysis, I mean, how do we minimize size and electron clouds? And by size, I mean electron clouds bumping into each other. And that's what sterics is electron clouds bumping into each other. So how do we minimize electron clouds bumping into each other? Because that normally leads to greater stability. Because essentially what we have here is that's a positively charged species. That's just, an abomination. And so what we have is an equilibrium between these two species. And yeah, it goes through this oxocarbenium thingy, but nothing stays there very long because it's a high energy intermediate. So if we're thinking about that, and I just redraw it, and I think we briefly touched on this earlier, but I kind of want to come back to it now because I actually have numbers in my back pocket, which is always handy in math. Now, the bottom one here is obviously not a real equilibrium. It's more we have a chair flip. And I guess you could argue that conformers are an equilibrium. But, it's a chair flip. The top one is actually also a chair flip now that I look at it because there's no other stereochemistry. But we can also do it through reaction. So what do you think? I guess where I'm going with this is what should the ratios of these things be? So I can tell you that the A value of OM of methoxy is, I've got it written here, 3.0 kilojoules per mole. I probably should have that in kcal because that's more useful. So it's slightly under one, it's about 1 kcal per mole, give or take. I can never remember what the conversion is, I don't care. But the A value of a methoxy group is 3.0 kilojoules per mole. So does anyone remember what an A value is?
So like the size, kind of.
Yeah. So what does it mean?
I can't remember exactly, but it's like you're comparing the size to something else.
Yeah.
And like the larger the number, the bigger the molecule compared to whatever I don't remember like what exactly you're comparing it to, but
so what it is,
Something like in the R and S conformations.
nope.
Okay.
What it is, it's the energy difference between these two species, these exact two species. A cyclohexane with a single substituent on it. What's the energy difference between having that group axial or equatorial? 3.0 kcal per mole. So that's the delta G of that process is 3.0 kcal per mole. The equilibrium, or the K, is equal to the concentration of, it's positive, I always get this wrong. You know what, we'll get the sign, well, maybe we'll get the sign wrong. Equatorial over axial. Concentrations of those guys. And we know that we are out of space. So I'm going to write this on a new page. So we go back to how we can relate delta G's and equilibriums. Delta G equals negative RT ln K. And that is equal to A. So the ratio of the two species is such, like, so we can actually solve for K. So if we do that, 3.0 equals negative RT log K. Great. 3.0 over negative RT equals log K. K equals E to the 3.0 over negative RT. I have written down that the answer to this is 0.3. So I guess I should say axial over equatorial instead of equatorial over axial. Can I remember which way it goes? So basically, what that means is if K is equal to 0.3, that means that you have about a 3-to-1 ratio of the equatorial to the axial in this molecule. Which, again, 5 kcal per mole or 5 kilojoules per mole is about a 5-to-1 ratio. So that makes about sense. It's pretty close. So anyways, you're favoring equatorial, this guy here, by a factor of 3-to-1. And that's what the A value means, is what, and that's how we can measure size, because bigger things are going to favor the equatorial more than smaller things, because the only thing that's determining this ratio is how big this is and how much this is whacking into the hydrogens at the other two axial positions. That's what's defining everything. So it's all about size. So sterics is all about the size of the clouds. I don't know why I capitalized the T. It's all about E minus clouds whacking into each other. And you can have sterics between molecules, you can have sterics within molecules. It causes electrons to repulse each other because they are negatively charged. Okay. So now let's think about this guy. So it's really similar. We've swapped out a carbon, a CH2 group for an oxygen. Okay. How does that affect the sterics of this system? Well, if anything, a lone pair is smaller than a hydrogen. And that's what we've got there. So if I'm thinking about this, I'm thinking, and if I'm comparing this to a cyclohexane ring, for this axial guy, I don't really see much of a difference in the sterics. Everything's pretty far away. For the equatorial, hey, this is a little bit close to this hydrogen. And now it's got a lone pair. So if anything, actually, the steric strain on the equatorial is actually less for this kind of system. And so because the steric strain is less, I would expect that I would even favor the equatorial more. On the other hand, carbon-oxygen bonds are slightly shorter than carbon-carbon bonds, which is going to compress the entire thing and going to bring everything a little bit closer together, which would make the axial a little bit more unfavorable, because suddenly this hydrogen here on my badly drawn, I'm going to redraw it because I'm offended by my own drawing. That vertex wasn't really vertexy. Is going to be a little bit closer to that axial OME than it would be in a cyclohexane. But I'm talking about angels on the head of a pin right here. So maybe on steric basis alone, I would expect somewhere between 2.8 to 1 and 3.2 to 1. Like whatever. It's different. I'm going to say yes, it's different. But who cares? It's about the same. Everything kind of washes out. So that was the thinking on this. And it's pretty surprising that the problem is that the ratio is the wrong way. 3.8 to 1 the wrong way, with the axial really favored over the equatorial. So the first time this was actually measured, everyone thought that they had actually gotten it backwards and that they had misassigned which one was axial and which one was equatorial. Because then it would have made perfect sense. Like whatever, 3 to 1, 3.8 to 1, basically the same thing. But that's not what happened. It's 3.8 to 1 the wrong way. So sterics don't work. So what we can think about is just let's do some quick math here. And I mean real quick math, not like the math I did up there, where we went, okay, this was 3.0 kilojoules per mole. 3.8 to 1 is about, 3.0 kilojoules per mole. What's a 0.8 between friends? You can calculate what it is, but who cares? But it's the wrong way. So this total difference is 3.0 plus 3.0 equals 6.0 kilojoules per mole. So this, under all the steric rules, should be about the same. The difference between these should be 0. It should be about 0. A tiny little difference. But it's not. It's 6. Because not only are we overcoming it to make them equal, then we're going 3.0 kilojoules per mole the wrong direction. Actually, something more than that. So there's some magic force that is inverting the selectivity and is worth 6.0 kilojoules per mole, which is, not chicken feed. Like, we're getting close to like the strength of a hydrogen bond here. Like, this is not meaningless values. What is going on?
Sorry, John.
Yeah.
What exactly is the 6.0 kilojoules per mole?
It's this magic force difference. So axial to equatorial is 3.0 kilojoules per mole. We're good with that, right?
Right.
Okay. So if these are going to be equal in population state, like let's say magically you saw that they were equal, then there must be some magic force that is making the axial 3.0 kilojoules per mole more stable than you expect it to be.
Okay.
But we're not only going to equal, we're going to 3 to 1 the wrong way. So that's where we get the extra 3.0, because we had 3.0 from being 3 to 1 this way. It takes us 3.0 to get to 1 to 1, and it takes us 3.0 to go to 1 to 3.
Okay.
Which is kind of what we have here.
Okay, so one's just the cyclohexane, one's just the sugar, like the
Right.
3.0s.
But exactly, but they're the wrong way, right? And I would expect on steric basis alone that they should be really similar. The equatorial should be favored by about 3.0. Because sterically, these are pretty similar. A sugar, a cyclohexane, whatever. But it's 3 to 1 the wrong way. Because in the cyclohexane, it's 3 to 1. That's for the cyclohexane. So it takes us 3.0 kilojoules per mole to get from 3 to 1 to 1 to 1. And another 3.0 kilojoules per mole to go from 1 to 1 to 3 to 1. So this total missing energy of this force is 6. So something is applying about 6 kilojoules per mole of magic to stabilize the axial versus the equatorial. So this is where we try and get explanation. So this is called the anomeric effect. Magic force, because we don't like magic in science.
Wait, does it have something to do with the dipoles then?
Yeah, that's one possibility. So there are 3 explanations. Dipole minimization. Charge repulsion. And stereoelectronics. So this latter one is much more recent. These two were the initial ones, initial explanations. And I'm not going to say that any of them are wrong. It's more that we have sort of three aspects of thinking about the same thing. And they are all kind of stereoelectronics. So we define sterics, so let's quickly define electronics. Charge stability. Orbital energy stability. Electrons in lowest orbitals. These are all basically in different aspects of the same idea. What we're trying to do is minimize energy in terms of where the electrons are and bonds formed that lowers energy, electrons in low energy orbitals that lowers energy, putting charges on atoms that stabilize the charge better that lowers energy. These are all electronic effects. And these differ from steric effects because steric effects are all about raising energy because electron clouds are bumping into each other through space. This is all about like the inner life of the electron and where the electron is currently residing and living. Okay, so let's take these in turn. I can change color. Okay, dipoles. So the argument that gets made here is, okay, let's think about two different sugars like this. And I'm going to give you, so what I've drawn is I've drawn these in these lowest energy conformations, both of them. I guess I'm going to be absolutely anal. This is kind of coming out towards you. It's kind of splitting the bond angle between these guys, trying to get as far away from both of those groups. This I've drawn pretty much bang on. It's coming out a little bit towards us, but it's almost kind of in the plane. It's not going to make too much of a difference. So just take a few seconds. I'm going to draw it in the plane just for simplicity's sake. And draw in this where the lone pairs are on those oxygens. On all four. Okay. So all of our oxygens are sp3. I'm going to use the convention that if I kind of dot an orbital like that, it's going back into the plane of the page, kind of away from me. And if I thicken the side of an orbital like that, it means it's coming out of the plane towards me. So I'm kind of using wedge notation. And I should probably actually draw the electrons as arrows because that's going to be a whole lot easier because dots get lost. So I'm going to make these orbitals slightly bigger because, not because they're bigger, but because it gives me more room to draw my arrows. So hopefully you drew something like that. If you drew this one coming out of the plane, that's cool too. That's fine. But hopefully your orbitals are more or less there. So let's think about where the dipoles are on each of those oxygens. So just take a second Draw your dipoles on each of the oxygens. Okay. So hopefully for this guy, your dipole is like that, going towards the middle of the lone pair. And so the argument that gets made here is look at the overall dipole of these molecules. And you get the overall dipole by adding the vectors of all the independent dipoles, right? So this overall dipole is kind of like that. Whereas this overall dipole is pretty close to 0. Those vectors almost directly oppose each other. And what we know is that minimizing dipoles is stable. So what you can think is that, well, let's think about what happens with this dipole. If you have, how can we accentuate this or affect this? So if we have a very polar solvent, say DMSO, versus nonpolar. You know, everyone's favorite nonpolar hexanes. In which of those two solvents are the dipoles more, is this dipole, this first one, because it's the one going with the dipole. In which of these two solvents is the dipole more stable? Or doesn't matter as much, I guess is what I mean.
In the non-polar one?
Okay. Why are you arguing that?
Because in the first molecule that we have, the natural dipole, the innate dipole of the molecule will be more, it will stay put when there's hexane and not disturbing the dipole at all, whereas DMSO can disturb it a bit.
So which direction would DMSO disturb the dipole? Would DMSO accentuate the dipole or stabilize the dipole or lower the energy of the dipole?
Well, if I think that way, DMSO might actually stabilize it.
Right. So do you want to
Yeah.
revisit your answer?
Yes.
Okay.
Yes. The polar solvents would give a better minimizing dipole effect.
Right. So strong dipoles are stabilized in polar solvents. And, you know, this shouldn't be surprising because what a dipole is essentially is charge separation in a molecule, right? You're basically saying I've got a positive side of my molecule and I've got a negative side of my molecule. And remember, I think the thing I always think about is molecules are stupid lazy and charges are heavy. And so no molecule wants to carry more charge than it has to. And so anything that can decrease the magnitude of the charge is always favorable. So if you have a polar solvent, you can imagine that, you know, for some reason I'm stuck trying to pick a color. Okay. No, I've already got green. Shit. Orange.
Go for yellow.
Now, yellow is unreadable. I wish
Go
I
for
could.
black for a change.
Yes, I could go for black. That's true. So a polar solvent, right, like DMSO, might arrange itself like this, and suddenly where you had sort of a delta plus on this side of the molecule and a delta minus on this side of the molecule, just from the inherent dipole, that is decreased by charge transfer with the DMSO. So you don't have it quite as positive because the DMSO is donating some electrons, and this one's not quite as negative because it can donate some electrons to the DMSO. So we're decreasing the charge differential across the dipole by having a polar solvent. So polar solvents stabilize strong dipoles. So what's interesting, and what lends support that this is a partial explanation for the anomeric effect, is that anomeric effect is more pronounced in nonpolar solvents. Which makes sense because remember, the anomeric effect is stabilizing this guy. And so in a nonpolar solvent, the dipole is going to be less stabilized. So more of the molecule wants to become this dipole canceling structure instead of this dipole with the two dipoles reinforcing each other, which is bad in nonpolar solvents. So dipoles seem to maybe fit the required definition of this. They partially explain it. The problem with the dipoles is nobody has ever seen a dipole effect this strong before. And secondly, well, that's mostly it, actually. Nobody's ever seen a dipole effect this strong before with something that's just, like, it's not charged. It's just oxygen atoms. Like, yeah, there's dipoles and I'm drawing big-ass arrows, but the dipole moment on these things isn't really that big. Okay. So the dipole moment is consistent with, but doesn't explain the amplitude of the anomeric effect. It is 453. Okay. So let's talk about charge repulsion. So again, quickly draw our sugars, our fake sugars. There we go. Okay, so we've got these lone pairs. And the lone pair is 2 electrons. And electrons don't like being near other electrons. And so in this beta form, I've got these 2 electrons are reasonably close, especially to this back lone pair here. So we have direct steric repulsion between them. And that's bad. The electrons don't want to be near other electrons, right? You can think about the electron cloud and how big the electron cloud is, and we've drawn it as a nice simple sp3 orbital, but we know that it's bigger than that, and there's like electrons all around this oxygen. And these guys are closer together than these guys. No major repulsion. So, yeah, it's a thing, but we're not talking huge electron clouds. We're not talking super close, and there's some rotation. So again, this is where we're talking about sterics and electronics. This is obviously sterics. electron clouds bumping into each other. That is literally what I am talking about. And the dipole stuff, well, dipole is really electronics. And because we're talking about charge stability, right? We're talking about where we want the charges in the molecule and how we don't want the charges too close to one another. And when we're talking charges, we're really talking about the occupation state of electrons in orbitals. We've definitely abstracted the orbitals here. We have not drawn any orbitals, except like the lone pair orbitals. But we really haven't talked about where the electrons are in the orbitals. So, one of the jokes, and it's not really a joke because it's kind of true, is that when I'm asked occasionally a seminar question, when I'm giving a seminar about the research we're doing, and I'm asked, why is that happening? Why is that chemistry happening? Especially with some of the crazy ass sugar chemistry that we do in our group, and I don't really understand. I always normally answer that the reason for this reaction is because of a complex interplay between sterics and electronics. And what I'm basically saying is everything under the universe is happening. I don't really know what's going on. Because everything is sterics or electronics. Everything is all about the stability of the charges or how, electron clouds don't want to bump into one another. And that basically explains all of chemistry. There isn't anything else. So we have an electronics explanation here. We have a sterics explanation here. And none of those was really satisfying. And so we came up with a complex interplay of sterics and electronics. And so we have a stereoelectronic explanation. Okay. So this is not the same thing as sterics and electronics. What it is about the geometrical orientation of orbitals relative to one another. On my notes. And we don't need multiplicity to tell me how to download itself. So what this comes from the idea of is if we're going to go back to this molecule again. I really hope you are getting sick of this molecule. Sorry, got that backwards. A is longer than B. D is bigger than C. And these are bond lengths. So we could rationalize this a little bit, but we start getting into trouble if we start trying to think about either of the other two explanations to try and explain these observations. That bond length B, the beta anomeric linkage, is shorter than the alpha anomeric linkage. And C is shorter than D. Now, B and D are roughly equal to each other, and they're also roughly equal to the bond length in methanol, like this bond length here. So that seems to be about the length of a normal carbon-oxygen single bond. But A is longer than a normal carbon-oxygen single bond, and C is shorter than a normal oxygen-carbon single bond. Okay, so what does that tell us? Well, are short bonds stronger or weaker than long bonds?
Stronger.
Right. Like, you make a bond shorter and shorter and shorter, eventually becomes a double bond, eventually becomes a triple bond. And then I guess you start doing some nuclear fusion or something past a certain point. But so what we know is that C is a stronger bond than D, and A is a weaker bond than B. So how can we explain this observation? So what I want to come back is I'm going to drop this for a second. And we're going to recall something. And this might not be recall for everybody because you might not have seen it before. But if you took second year first course second year organic 1 with me, you would have. And I don't think either of my colleagues who teach this course on a regular basis use this. But let's just think about the E2 elimination. So if you remember what an E2 elimination is, proton, leaving group, base grabs hydrogen, electrons in a hydrogen carbon bond form a new double bond, leaving group leaves, you make a double bond. Right, that's the E2. Elimination, biomolecular, so you need both the base and the thingy with the leaving group and a hydrogen in it in the transition state, in the rate determining step. So the other thing is we know that you need to have this anti-periplanar thing, so hopefully that rings a bell. Which means, what do I mean by that again? Just as a reminder, that this H and this Br, these lines are 180 degrees from each other, pointing in the other opposite direction. So they are anti because they are 180 degrees, and they are periplanar because they're not twisted out of alignment. They are directly in alignment. And so why is that necessary? Well, it's necessary because these arrows are not really telling what's going on here. I'm going to skip to the next page. So what we have, if I'm just drawing this real simple like, this is our sigma orbital. It is the highest energy orbital in the molecule. The highest energy orbital of that molecule I showed you was to be the carbon-bromine bond. Carbon-bromine is the weakest bond. Everything else is carbon-carbon, carbon-hydrogen. Those are nice strong bonds. Carbon-bromine is weak. So for every bonding orbital, there is an antibonding orbital. What does the antibonding orbital look like? It does not look like what I'm about to draw, but close enough. And I don't really want to get out a computer simulation program for this because that's just weird. Remember, I never draw in the lobes, little lobes for the SP, but you have an antibonding orbital. There are, of course, electrons in the bonding orbital. And the lobes are out of phase. Like this one is filled. This one is open. It's a little sp3 lobe there on this bromine. And there's no bond interaction there, right? Because the lobes are out of phase. So there's no interaction there. Now, this normally doesn't matter. That orbital is empty. So who cares? I guess it exists in theory, but nothing is using it. There are no electrons in it, so we can ignore it. And everybody can be happy that they've made a bond. But when a base is coming along, just keep this in mind. When a base is coming along to grab this proton, whee, base. And, I'm just going to draw the bromine off at some angle because it's just, it's partying and it's just rotated off and it's doing whatever it wants. So the base comes in, uses its lone pair to grab this hydrogen. there are 2 electrons in this hydrogen-carbon bond. I'm sticking them both in the carbon orbital right now, but they're kind of, we're doing linear combination of atomic orbitals here, right? So, but there's a whole bond and the electrons kind of spread over the whole thing. And we're massively simplifying it by just drawing LCAOs, but we're trying not to lose our fucking minds. So base comes along, grabs that proton. Hydrogen can only make 1 orbital bond. The base is actually dumping electrons into the carbon-hydrogen antibonding orbital. That's what it has to do. To break a bond, you need to put electrons into the antibonding orbital. Otherwise, you're not going to break the bond. So that's what the base does, and that's how it gets the hydrogen, is it puts electrons into that antibonding orbital. But let's think about that for a second. Where this is transitioning, I'm not going to draw, the bromine is still doing its thing off at some angle here. And we have base hydrogen. And now we have a C minus. Let's make the base something specific. Let's make it OH minus. That is not a favorable reaction. You have traded an OH minus for a C minus. That is shit. Like, that is a bad trade. No molecule is ever going to do that. You are never going to form that C minus. It's impossible. But the antibonding orbital of the entire system looks a lot like this. As that base is coming in and grabbing this hydrogen, and you're getting these 2 electrons here, because now we have 2 extra electrons in the antibonding orbital of the entire molecule. We just got those from the base. They stripped off the hydrogen. Now we have these. These guys don't need to actually sit on there as a C minus because they've got this nice big juicy empty carbon bromine bond right there. And yeah, that's sp3, that's sp3, and you don't make a bond between 2 parallel sp3s. You do that with p orbitals. But these electrons can start donating into this bond. And of course, this is the antibonding orbital, so we're putting electrons into this, so we're breaking the carbon-bromine bond. And this is how the E2 works. So this sigma star slowly converts. Well, not slowly, it probably happens in femtoseconds, or whatever's faster than a femtosecond, to a pi orbital, where now the bromine is gone. And it's taken its 2 electrons off with it to play. So we've lost the 2 electrons from the sigma bond because we have broken that orbital because we have put electrons into the sigma star. But that was only possible because this antibonding orbital, this major lobe of this carbon-bromine antibonding orbital, was perfectly aligned with this carbon orbital. Because if it's not, you have a situation like this, where these electrons have got nowhere to go. Like the antibonding orbital of this carbon-bromine bond over here is down here. And that's where all the electrons are. That's where all the capacity for storing it. And these just don't line up. So this is a stereoelectronic effect that we're talking about here. The E2 elimination, the definition of why you need that antiperiplonarity is because of stereoelectronics. It's because of the geometrical arrangement of the orbitals that contain the electrons. And for the E2 to happen, what needs to happen is that the charge, the electrons, the stability of these electrons requires the geometry of the adjacent orbital to be lined up with it perfectly. Otherwise, nothing happens. Okay. So that's where we're talking about stereoelectronics back here, a few slides back. Geometrical orientation of orbitals relative to one another. That defines what stereoelectronic effects are. So, what the hell does this have to do with this whole sugar thing? Well, let's think about it. Because what we've done here is a reaction with the Z2. We've done an extreme example. But let's think about what's going on with an alpha linkage. Okay. What's the weakest bond in this molecule?
Is it the CH?
Nah, CHs are fucking rock solid. That doesn't give us many more options, actually, does it?
Yeah, I was gonna say my next guess would be the C, like the carbon-carbon bond.
Oh, no.
No? Okay. Well, I
Paul
don't
has now exhausted all of the other options.
know.
Does anyone want to take the layup he set up for them to just like finish this into the net? Even I couldn't miss this one.
The carbon
CO1.
oxygen one.
Boom!
CO1.
Carbon oxygen. Exactly. That's the only thing we've got left. The weakest bond in here is carbon oxygen. Now remember why that doesn't. This shouldn't be too surprising because we've just been drawing all these oxocarbeniums. Like when we broke bonds here, we broke the carbon oxygen bond. Actually, let's keep this oxocarbenium in our mind because let's think about an extreme case. In an extreme case, and to be fair to Paul, this was a trick. It wasn't a trick question, but it's not a trivial question if you're not used to really thinking about that. So, Paul, thank you for answering. But let's throw a proton on here. Okay, now the weakest bond here, just so we're absolutely clear, is definitely the OH bond that we formed because that's really weak. But the second weakest bond is we know that this can go back and forwards to the oxocarbenium because we've just been drawing things like that. So mechanistically, how does that happen? How does this go to the oxocarbenium mechanistically? It goes there because let's just think about what's going on here. I've just said that this is your weakest bond after the OH bond. Well, this is obviously a sigma orbital I've drawn here. So what does a sigma star orbital look like? Well, if this is the weakest bond, let's draw the antibond of that. And that would be a giant empty lobe here. This is going to be absolutely I guess there's still electrons over here. But it's going to be absolutely, because we can redraw that, because you can draw a bond like that, or you can draw a bond through a linear combination of orbitals, right? It's an equally valid way. It's a stupid way to draw a bond. You don't want to go doing that. It's just really confusing. Draw a freaking line. But that's what that means, is that the like a bond means that you have an sp3 lobe coming out from each of those atoms if you believe in sp3, if you believe in hybridization, and that they're kind of interacting together to make a bond. So the antibond is got to be absolutely the opposite direction, just like in the E2, just like in that bromine bond, it's pointing the wrong way up. And now if we notice, ooh, this looks kind of like that E2 situation I had. I've got this big, juicy, empty orbital, and I've got electrons in this orbital. And if they donate into this orbital, they're going to make a double bond, oxocarbenium, and you're going to break that carbon-oxygen bond. And you're going to release methanol. And that's what happens. And that's what this is always existing. Now, the example is really, really clear over why that bond is so weak when you protonate it. But that antibonding orbital is always there. And if there's two things that we know about electrons, is that electrons always want to be neutral. You always want to stabilize charge. And electrons have wanderlust. Electrons want to be everywhere at the same time. Electrons do not want to be penned up and caged. They want to be free. They want to be in multiple places. So if you're a lone pair electron on this oxygen and you're in your little orbital and you want to see the world, and you know that, even without that hydrogen there, even with just this guy, the neutral guy, you know that there is a higher orbital sigma star that exists. Where, it's empty, it's huge, it's juicy. You're not going to put all your electrons in there. You're not going to break the bond. But, maybe you can sneak out of the house a little bit and you can share some of your electron density into this nice big juicy orbital. And it's a nice weak bond. The CO bond is weak. It's screaming, like its big, empty, juicy orbital is screaming for a little bit of electron love. And you got the electrons, and you can share, and you can be in a couple different places at once, and you don't want to be locked down in your own little orbital because you're a wanderlust loving electron. This is what's always happening in molecules constantly, is electrons in lone pairs are always kind of shuffling some of their density into adjacent antibonding orbitals of everything. And the stronger, the better the leaving group, the more polarized the bond is adjacent to it, the lower lying that sigma star is going to be. Like when this thing is charged with that H like that, that's a really low lying sigma star. It's really easy to access it because that OH, that methanol is a really good leaving group. And so making that double bond is really easy because it's a really good leaving group. And if making a double bond is really easy, that means that it must be easy to access that sigma star. Because if it wasn't, making that double bond would not be easy. All these things are tied together. It's not like one causes the other. They're all basically different ways of looking at the same thing. But even when there's nothing helping us pull this bond apart, there's no charges, the oxygen's not charged, you still have that juicy, empty orbital there. So at any one time, some of that electron density in that lone pair has donated to that antibonding orbital next to it. So what is that going to do? Well, it's going to increase the bond order between this oxygen and carbon because, yeah, we got the single bond of the sigma bond, but now we've got this other kind of out-of-plane interaction is also occurring. It's not a full pi bond. We're not making a pi bond, but we're getting into this gray area between what is a single bond, and what is a double bond. We're now at like a 1.05 bond. We're a little bit more than a single bond, nowhere near a double bond, but there is this additional interaction. And because our bond order is increased, our bond length shortens because that electrons suck the other carbon closer because they're kind of making a bond, and every time you kind of make a bond, you shorten it. And at the same time, what you're doing is you're not putting electrons into the antibonding orbital, but you're not putting electrons into the antibonding orbital. You're putting in like a tiny fraction of an electron density into it. You can think of this in lots of different. If you're like a quantum person, I'm not. But if you are a quantum person, you can think of that you have a probability of population of the antibonding orbital of about 5%. So at any given time, about 5% of that orbital is occupied, and you have a 5% probability of that happening. If you're more of an analog person, I think this is more the way I think of it. It's kind of like a little bit of the electron is in there. And of course, that makes no sense. An electron is a thing. But electrons are wave functions and they're probability functions. And so I've got a lot less trouble with sharing a bit of a probability function and sharing like a particle. And electrons are definitely not like behaving purely like particles. And so at any given time, a little bit of the electrons in the sigma star, which is going to strengthen this oxygen-carbon bond because it's starting to move towards a pi bond, like we saw with the E2. And at the same time, that's going to weaken this sigma bond. And so this bond is going to weaken. And another way of saying a bond is weakening is by saying the bond is lengthening. And so this bond, I would expect this bond to be longer, and I would expect this bond to be shorter. And that's exactly what we observe. And what we can actually do is a whole lot of things. This is where the stereoelectronic effect was first proposed, was to explain this anomeric effect. Now it's basically can be used to explain almost all intramolecular reactivity. And I will always fall back on a stereoelectronic explanation of almost any reactivity because it actually explains everything all the time. The dipoles don't explain everything because sometimes you have things that go against dipoles, but you never really have anything that goes against the stereoelectronic effect. So what you can expect is that bromine, very weak, very strong anomeric effect. It is basically impossible to make beta bromides. You cannot make the beta bromide because the anomeric effect is so ridiculously strong for bromine because that carbon-bromine bond, it's almost like an ion pair. It's almost like a C plus Br minus. It's almost not covalent anymore. It is, but it's right on that edge. And so it has this humongous, juicy, empty antibonding orbital, and the electrons from the oxygen lone pair are just constantly donating into it. And so it's almost half an oxocarbenium. This bond length is really, really, really short. This bond length is really, really, really long. And so the better the leaving group, the stronger the anomeric effect. And dipole-dipole interactions don't explain that always. Charge repulsion things don't always explain that. But the stereoelectronic effect does explain that exactly, because that's exactly what you would expect. So we're at 522. I'm going to leave it there. So when we meet next class, we're going to talk a little bit more about the anomeric effect. We're going to talk about the exo versus the endoanomeric effect. And we're going to talk about the reverse anomeric effect, which it doesn't really exist. Yeah, there's no homework for the weekend. What I will start doing, I think, is I will start posting the assignments online and get my acting gear. I'll do that probably over the weekend or Monday at the latest. And as I said, the midterm and exam will be drawn from assignment questions or very slight modifications of the assignment questions. There won't be any marking scheme for the assignment questions provided or any answer key. So it's a good idea to go through them. I recommend you try them on your own, and then you can work with other people. If you're really stuck, come to me and I can point you in the right direction, but I'm obviously not going to give the right answer. So I'll start posting those on Monday, and you can start going in. I don't think I have very much on there right now that you could answer based on the lectures we've seen. By Monday, maybe I mean tomorrow. I might start. I'll probably post assignment 1 tomorrow, and I'll try and post these all the lecture slides tomorrow as well. Okay.
John, one quick thing before we end, just going back to the glucose thing.
Yeah.
So they knew that like D-glucaric acid was octavely active, right?
Yes.
So yeah, I'm just remembering like what I actually like my logic, I guess.
Do you want to come back to this on Tuesday then?
Yeah, that's fine.
Or are you going to forget your logic before then?
I
always forget it, so I can completely understand.
It's okay. I'll just write a note and then.
Yeah. Okay. I want to just check it to make sure I can confirm with you.
No problem.
Instead of going sounds good and then be wrong. Okay. Cool. I love stereoelectronics. I don't think I completely understand them. But they make a lot of sense for how things work. And so we have to always be thinking about the geometry of orbitals. And I think that that's true in chemistry. So I think it's a useful thing to be thinking about and talking about. But it's my preferred explanation for why the anomeric effect is as strong as it is. Okay, I will end here.